Well, hello again. I'm going to talk about the ideal gas law. This says if I have a container that contains a gas, container has some volume V, gas at some pressure P and temperature T, then those are all related by PV equals nRT. This is actually not a fundamental law of nature. It's really just a very good approximation. So let me clarify here. P has to be absolute pressure, and it could be in units of pascals, and I'll remind you that's newtons per square meter. Volume would be V is volume in meters cubed. N is number of moles. T is absolute temperature. So that's temperature relative to absolute zero in kelvins. So K. And R is something called the ideal gas constant. And using this set of units, that R is 8.314 joules per mole Kelvin. So if you know any three of these, you can solve for the other one. I will not insult your intelligence by just plugging those in and solving. I will do an example in a little while of when these change. This is not the only possible set of units, though. You could also have PV equals nRT. And this will work if P is absolute pressure in atmospheres, V is volume in liters, see, N is still number of moles, T is still absolute temperature in kelvins. And this will work if you use the ideal gas constant R as 0.08206 liter atmospheres per mole Kelvin. So that's just another way to use the equation. It's just a different set of units, and the R is just changed to use that set of units. There's yet another way to do it. Well, there are other ways too. There's another way that's actually often used in physics. I would say these are probably more the way that it's done in chemistry. Let me show you another way that introduces another important constant that will show up pretty often. So before that, I need to remind you of what number of moles, how number of moles is related to number of molecules. If N is number of molecules, and N sub A is Avogadro's number, .02 times 10 to the 23 molecules per mole, then we have big N is little n times Na. This just says the total number of molecules is the number of moles times Avogadro's number. That's really a definition of a possible definition of Avogadro's number. So this means this little n is big N over Na. So this means that PV equals little nRT can be written as PV as big N over NART, but both R and NA are constants. So we could write that as big N R over NAT, and this R over NA we're going to define as a new constant. Lowercase k is R over NA. That's 1.38 times 10 to the minus 23 joules per Kelvin. So this is a little k. That's a big K. This is something called Boltzmann's constant. And it is really quite pervasive in physics. It shows up all the time. So now this becomes little k, and the ideal gas equation becomes PV is big N KT, and that's another way of writing the ideal gas equation in terms of number of molecules. And then this product KT shows up really quite often in physics. That product is a thermal energy. So this is just another convenient way of writing the ideal gas law. So let me do an example for you. If I can turn the page, which is, all right. So, example. So I've got a tank, as you would expect. This tank contains 2 atmospheres, absolute pressure, of some gas that's approximately an ideal gas at 30 degrees C, and half of the gas leaks out of the tank. And it leaks out rapidly so that the tank cools. And it cools to minus 10 degrees C. What is the new pressure? A, what is new pressure? And B, how many molecules leaked out? All right. Here's the way you typically do this. When you're doing the ideal gas law and things are changing, you write the ideal gas law twice in terms of the initial situation and the final situation. It's actually called an equation of state, provided things, so they're just true at any given instant. That's what I was trying to say. I got into that sentence and couldn't quite finish it. So at the initial situation, we've got P1 V1 is N1 KT1. That was true at the start. And at the finish, P2 K2, P2 V2 is N2 KT2. That was true at the end. So I'm going to divide this equation by this equation. That's valid mathematics. So I've got P2 V2 over P1 V1 is N2 KT2 over N1 KT1. Now I can cancel all of the things that didn't change. The volume of the tank didn't change, K didn't change, the N's did, the T's did, the P's did. P2 is what I want, so I solve this for the thing I want, P2. So P2 is P1 N2 over N1 T2 over T1. And I know all that. So P1 was 2 atmospheres. That unit works perfectly fine now. For the atmospheres there, I'll get atmospheres there, provided it's absolute, and I did say it was absolute pressure. N2 over N1. Well, N2, since half of the gas leaked out, N2 was half of what N1 was. So this is 0.5 N1 over N1. So the N1s will cancel. T2, T2 was minus 10, so that's 273 minus 10. That's how you convert from Celsius to Kelvin. It's 263 Kelvin. T1 was 30 Celsius, was 273 plus 30 is 303 Kelvin. Is that right? Yeah. So this gives me 263 Kelvin over 303 Kelvin. And if I multiply all that out, I get 0.0868 atmospheres was the pressure at the end. Now I also wanted to know how many molecules leaked out. So for that I actually have to know how big the tank was. And I didn't specify that, so I've got to, let me go back and change the question. If it's a 25-liter tank, how many molecules leaked out? So we know half of the molecules did. So let's see. The volume of the tank, what we're going to do, we're going to use PV as NKT. So N, so we're going to compute how many molecules we had, and then say half of them leaked. So N was PV over KT. So we need P, we need K, we need T. So as an aside, I need V. So V is the volume of the tank, is 25 liters, times a cubic meter is 1,000 liters. So that's 0.0250 cubic meters. And this becomes pressure, it's 2 atmospheres, is 2 atmospheres times 1.013 times 10 to the 5th pascals per atmosphere times the volume, 0.0250 cubic meters, over K is 1.38 times 10 to the minus 23 joules per Kelvin, times T in the beginning was 303 Kelvin, we just did that. That gives me 1.21 times 10 to the 24 molecules. So that's how many I had in the beginning. Half of those leaked out. So the number that leaked is 0.605 times 10 to the 24 molecules. All right, so again, just to reiterate, if you're using the ideal gas law and it's changing from one state to another, one situation to another, write the initial situation, the final situation, divide the final by the initial, and solve for the part you don't know. Okay, it's pretty straightforward. I will see you soon.